grouping hopefully will work. So to find our zeros, try to factor. Pull out an x squared, left with x plus 3. Pull out a negative 1, left with x plus 3. We have x plus 3 times x squared minus 1. And that difference of perfect squares goes a bit further into x plus 1, x minus 1. So our roots are at negative 3, 1, and negative 1. And so that would begin my sketch. Negative 3, negative 1, and 1. Check. Is this an even degree or odd degree polynomial? Odd. Okay, so our end behavior has to be opposite each other. And because it's positive odd, it's got to have an overall positive slope. So it's going to start low and high. So we're going to start down here, and then we have to hit every root. So we should have a y-intercept just based on our quick sketch there that is what? Negative. And we can just confirm that, and I usually just like to scale the graph to fit my picture. So we're going to label that y-intercept what number? Negative 3. Your y-intercept is always your constant at the end of your polynomial. So that's just negative 3. Now, as we get into calculus, we'll talk more about how to label or figure out our relative maximums and relative minimums. You do not have the skill. Some you might get lucky with for a different reason, but you don't yet have the skill to be able to determine the relative maxes or relative mins, but we will work on that once we get to calculus. If the graph is symmetrical, then you'll find some success. Like here, you may get lucky because the relative maximum might be perfectly halfway in between those. So it might be at an x-coordinate of negative 2. And then when you plug in negative 2, you'd find your relative maximum point. I'm not positive if that's going to happen here. It seems to look like it's going to, but it won't happen like that all the time. And so we'll look at how to actually use a technique that will work all the time. All right, what do we have on the back? Okay. Showing that this polynomial has a real zero between 2 and 3, or has a root between 2 and 3. Now, I've given you a function here that's not factorable. Has everyone seen that? Not factorable. So it's not like I can just factor it, find my zeros, and get that one of them is 2.3 and know that, there we go, it has to be between 2 and 3 because I found it. So given that we can't factor it and find our exact zeros, what could we do to prove that this graph will hit a 0 somewhere between 2 and 3? There's 2, there's 3. How are we going to prove that it's going to cross the x-axis, either, maybe doing that or doing that? Not knowing what the rest of the polynomial looks like could look like anything. How could we do some calculations to prove it? Josh, what do you think? You're on the right track. I don't like your logic beyond plugging in 2 and 3, but I do like the idea of plugging in 2 and 3. Very good. So if you plug in 2, let's say you get a positive number. So 2 comma something will be a positive point. Then you plug in 3 and you get a negative number. You'll get 3 comma a negative point. Then somewhere in between, since this is a polynomial and smooth and continuous, and it will have to just connect those 2 points, you're going to have to cross the x-axis. Or vice versa. You might get a negative first and then a positive afterwards. Very good. So f of 2 is going to be 8 minus 4 minus 5. What's 8 minus 4 minus 5? Negative 1. And f of 3, when we plug that in, we're going to get 27 minus 6 minus 5. 16? Okay? So perfect. So f of 2, we got a negative number. And f of 3, we got a positive 16. I mean, I guess how close to 0, like Josh, back to your point, is somewhat relative. Is negative 1 close to 0? You could get a negative 52 and a 167, and neither of those are close to 0. We wouldn't say, but if you were talking about feet in outer space, that would be really close if an asteroid came 160 feet from the Earth. Right? So saying like how close something is to 0 is very relative to the context of the problem. So we're not going to go that way, but yes, one of these is negative, and you'd need a little statement to say that. So since f of 2 is positive, f of 3 is negative, and polynomials are continuous, f of x must equal 0 at some point between 2 and 3. This concept we'll do, gosh, I can't even remember what it's called, is it the intermediate value theorem? There's a theorem in calculus that we'll do that will get at this exact same concept. This really is what this is, but without calling it that quite yet. What we can do with this is say approximately, where is your 0? Is your 0 going to be closer to 2 or closer to 3? Would you guess, Connor, to what and why? Right. So because that point is closer to 0 than that one, you would say that your 0 is probably going to be closer to 2. Just for the sake of me being curious, I want to see exactly where it is. Second trace, 0, left bound, right bound, enter. 2.09. So yeah, definitely closer to 2. When you see a polynomial graph that's got a little kind of relative minimum without having zeros on either side, right? So we're not like crossing 0, just like a little fluctuation in the graph. What does that tell you? Do you know? Yep. From what? I mean, I guess anything is shifted in some sense. Like this is a cubic polynomial, so knowing that our cubic parent graph looks like this, right? Everything is going to be probably somewhat shifted, or let me be more specific about what I'm getting at. What does it tell you about the roots? How many roots should this have if it's a third degree polynomial? 3. And you only see one of those roots, right? Typically fluctuations kind of will cross on one side and cross on the other and cross again, so you have your 3 visible roots. So if you have a little kind of fluctuation in the graph, but it's not causing any more roots on either side of it, what can you gather from the nature of the roots? They're imaginary, exactly. So this I can see has 1 real root, which we just found, and then 2 imaginary roots. Did you know that? Does that sound familiar? Yeah, hopefully. So I guess down at the bottom, what I mean by that is if you have something like this, and the same is true if a graph never, like if I give you an odd degree polynomial, or an even degree rather. How do you know what degree that is just by looking at it? Normally you'd count the roots, right? And if there were 4 roots, you'd say it's a 4th degree polynomial. This is clearly not a quadratic, right? If it's got a degree of 2, then how many relative maxes and mins does it have? Right, relative extremes equal 1. So if your relative extremes, and how many do we have here? 3. This is a degree of 4. Did you do that last year? Just kind of maybe we're going a little bit deeper into patterns that you should pick up on. If you have a degree of 3, you'll have at most how many relative extremas? 2. And we can see them here. 1, 2. You don't have to have 2 though, and you don't have to have, 1 or, well, with a degree of 2, do you have to have 1? You have to. With a degree of 4, do you have to have 3? You don't have to have 3. But this is kind of an at most sort of number. At most, you'll have that many extrema. And the reason, if we go back to our parent graph, you don't have to have 2 relative extremas. Obviously, this is a cubic polynomial, and we don't have any relative extrema. Do we see that? If you happen to have a triple root, and it's all the same root every single time, so you do have 3 roots, but it's the same root all 3 times, you're going to lose relative extrema that way. Same thing is true with a 4th degree polynomial. If you have something like this, that's not going to have 3 relative extremes, right? It's a 4th root at 2. Does anybody know what that looks like? So it's got 4 roots. It's just at 2 all 4 times. Well, you guys know what this looks like, right? If it's a double root, you know what that looks like? It bounces. A 4th root bounces, but a little more flat. So it would kind of look like that. Okay, I'll show you on the calculator. It'll become more clear. If I do x minus 2 to the 4th power, it's still going to be a bounce of sorts, but it got a little flatter than a typical parabola. Does that make sense? And if I make it a 6th root, it's going to be a bounce, but it's going to be even flatter. Okay, got skinny. It's hard to see when they're on top of each other, but if I zoom in to what's happening at 2, there's my 1 to the 4th power. And then there was my 1 to the 6th power that came down and kind of got flatter a little bit earlier over here. I'll zoom in one more time. There's the 4th power one, and then here comes the 6th power one that got a little bit flatter. So anything that's a 4th root, 6th root, 8th root, 10th root, they're all bounces. They're just flatter. And the same is true for cubic functions. Do you know what do you call this sort of activity? If you saw a cubed root or a triple root with a multiplicity of 3, did you talk about that? No? Did you ever do triple roots, multiplicities of 3 last year? Yes? What did you call this? It wasn't a bounce. Obviously you called the square a bounce. You didn't talk about it? Okay, well, I call it a wiggle, for lack of a better word. Bounce isn't really a mathematical formality, neither is wiggle, obviously. But just something to get you to know that it kind of does that wiggling look, and it kind of looks like it's going to turn around, but then it does a quick little maneuver and flips back up. So any odd root is going to do that. So obviously, let's put a triple root at 3. That's what, oh shoot, I zoomed. Hold on, zoom, 6. There's a triple root at 3, so it wiggles through it. If I make that a 5th root, it's still going to wiggle through that root of 3, but it's going to be a little flatter again. So I guess in compare, you'd have to see them side by side. It gets a little flatter. If I do x minus 3 and make it a 7th root and graph that, it's just going to get a little bit flatter. So if I zoom in, you'll see it. Get over here, zoom in. I'm going to zoom in twice. There's the 5th root. Here's the 7th root. I'm going to zoom in again. There's the 5th root wiggling through, and here comes the 7th root. It came over here, and it was already flatter. And then it came out over here on the bottom side. Anyway, we follow that? Okay, so that's your multiplicity discussion. So I will write, oh geez, what should I write? Multiplicity equaling even is a bounce, gets flatter as multiplicity increases. And if your multiplicity is even, or is odd rather, we are going to call that a wiggle. And same thing, gets flatter as the multiplicity increases. Okay, so I guess we're probably expanding into higher multiplicities than you maybe did last year. Sketching this graph, if we're going to get the roots, we're going to try to factor, and this factors into x squared minus 1 and x squared minus 1, which further factors into x plus 1, x minus 1, x plus 1, x minus 1, which is more condensely written as x plus 1 squared and x minus 1 squared. So how many roots do we have? 4. Each has a multiplicity of 2. So we have a root at -1 with a multiplicity of 2, aka a bounce. And we have a root at 1 with a multiplicity of 2, aka a bounce. So here will be -1, here will be +1. And we're going to bounce off of both of those points because we are an even degree or an odd degree polynomial. Even, our end behavior is the same on both sides, and we start with a positive coefficient of an even polynomial. So do we start low or start high? High. Good, opens up. Okay, so we are going to bounce off of this one, and we're going to bounce off of this one. And based on our quick sketch, we can see that our y-intercept should be positive, and it is +1. So I just then, again, I like to scale my graph to fit my picture versus scaling first and then messing around with your sketch. Just makes it easier. Okie doke. Any questions? Good review.